derivative of your vector valued function, it tells you the tangential trajectory of that particle at that time. That depends a little bit on how fast the particle is going, but also on the direction. To show you what I mean, consider this vector valued function that has got a sign. Oh, I mixed it up. I have the sign in the x coordinate and the cosine in the y coordinate. The parameter or parameterization side is a pi times t squared, pi times t squared. That does draw out a circle that you see here. The vector valued function, just to let you know, I accidentally put cosine in the x coordinate and sine in the y coordinate. It gives you the same idea, so I'm going to continue with this mistake. But the point is that the vector valued function is you plug in a value into your t, it tells you a vector that represents the position, the terminal point of that vector represents the position of the particle at that moment in time. You could take the derivative and figure out where that tangential vector is. This one shoots way off the screen. If I press play so you can see it moving in motion, it happens to have a negative time parameter plugged into this equation with the square. So that kind of explains what you're looking at. But if you go, it looks like it's moving very, very, very fast. As it gets closer and closer to 0, you can see what happens to the vector valued function. It is pointing tangential to the circle, but it just keeps getting smaller and smaller the slower the vector, the slower the vector valued function goes, so the parameterization goes, until it hits to 0 and then it becomes 0. And it becomes a positive, and then it switches the direction. I press play, you see that as it goes faster and faster, the vector value function just becomes so huge it's off the screen. Notice that if I go ahead and try graphing a different vector value function, I didn't change the names here, I'm just graphing a different vector value function by just changing the parameterization. So instead of a t squared, I just put a t and t here. So that's what I did here in GeoGebra. I just changed these to t, not t squares. I get the same curve. It's still describing a circle. If I press play, though, you can see the motion is going to be different. It looks pretty consistently. You can see the tangential vectors pointing in the direction tangential to the circle, but it's staying the same length. Sorry, my timer is going backwards in time, so that's why it looks like it's going the wrong direction. You can understand that as the vector valued function is telling you, you can understand the derivative or the tangent vector for your vector valued function is telling you how fast it's moving and in what direction at that moment in time. What if you were only interested in the curve information and not the speed of the particle? Could you get that information? The answer is yes. You could just normalize the tangent vector by dividing the derivative or tangent vector of your vector valued function by its magnitude. This will give you just the tangent vector, not how fast the particle is going. It doesn't really depend on the parameterization. There's one problem you have to avoid. You can't divide by 0. You can see now that for the old parameterizations, when I had a t squared inside the circle, that tangent vector is shooting off really long. The unit tangent vector, or the principal unit tangent vector, is just of unit length in the direction of the circle. This tells us just the geometry information of the circle itself and not how fast the particle is moving. It doesn't carry that information. So if we want to measure things about the path, like the length, we really want to be using formulas that use the unit tangent vector. To compute the unit tangent vector, regardless if it's in a plane or a three-dimensional space, you've got to find the derivative of the tangent vector, then find the magnitude of the... To compute the unit tangent vector for a vector valued function in 3 space or 2 space, you just have to take the derivative of the vector valued function, find the magnitude of the derivative of the vector valued function, and take the ratio of the two, and just avoid all points or find all points where that magnitude is equal to 0. For this example, we have the vector valued function here that describes a curve in 3-dimensional space. Its derivative is also going to describe the tangent vector along that curve at any moment in time. But that tangent vector will be length dependent on how fast the particle is going at that moment in time. You can think of the magnitude of that tangent vector as actually being the speed at that moment in time. So if you had a speedometer on that particle, it'd say, oh, it's going this fast at whenever that time is t. If you were interested in just the direction and not the velocity, you would take the derivative or the tangent vector divided by its magnitude, and that will give you just the direction information. What we have in the end is the unit tangent vector, where it's the tangent vector divided by the scalar magnitude. Both are a function of time, but there is a scalar in the denominator over here. We also call this the principal unit tangent vector or the principal tangent vector. They mean the same thing.